welcome back. In today's lesson, we introduced some new transcendental derivatives, and I know you're not going to be able to memorize them right away, but hopefully as you work with them, just like all the other transcendental derivatives, they'll come with time. So tonight's homework is going to have some of those transcendentals on it, but in general, tonight's homework is going to be kind of a broad overview of a lot of topics that we've covered this year. Sometimes it's good to go back and review topics that we haven't talked about for a long time, just to make sure you don't forget how to do those kind of problems. So number one says determine the derivative for each of the following. And we're going to start off here with some chain rule. So y prime is going to be the derivative of sine, which is cosine. So we're going to have cosine of cosine x times the derivative of cosine x, which is negative sine x. Now, kind of noticed most of y'all have started cleaning this up a little bit when you say like times a negative, but I kind of think that we need to move in the direction of bringing that negative out to the front, just so that we can avoid forgetting to write the times. So I'm going to bring that negative out to the front here, and you should start to do that on when you work these problems as well. Part B, we've got sine times cosine. So on part A, we use the chain rule, and part B, we're going to use the product rule. So we're going to have the derivative of sine, which is cosine, times cosine, plus the derivative plus sine times the derivative of cosine, which is negative sine. Now, I'm going to simplify this a little bit, and I know we've worked quite a few problems throughout the year where I try to emphasize that you don't need to simplify, but I also want you to be comfortable working multiple choice items along with the free response. And on the free response, as we know, we don't really need to simplify, but I want to look for opportunities to simplify so that when you do have to do that for the multiple choice items, you'll be in good shape. So here we've got cosine times cosine, that's cosine squared. And here we have minus sine squared. All right, we could potentially use, I forgot the prime there, we could potentially use some Pythagorean identities to simplify this even further, but I'm going to leave it like that. Part C, I'm going to move all this stuff out to the side here. Let's give us a little bit of room here. We're going to differentiate implicitly. So we're going to do a little product rule up front. 2 times 3 is 6. So you have 6x squared times y plus 2x cubed times dy dx plus the derivative of 4x, which is 4. And then we're going to differentiate 3 tangent y. So the derivative of tangent y, secant squared. And we're going to need to, we're going to run out of space there. Let me bring this out a little bit to the left here. It's 3 secant squared y times the derivative of y, which is dy dx. Now here, if we're trying to isolate dy dx, I'm going to need quite a bit more room here. I'm going to zoom in and, yeah, how am I going to do this? I should have done that from the beginning. All right, here, we're going to start this one over. All right, let's try this again. So we're going to have 6x squared y plus 2x cubed times dy dx plus 4 equals 3 secant squared at y times dy dx. Now we're going to try to move all the dy dx's to one side and all the constants to the other. So I'll have 2x cubed dy dx minus 3 secant squared y dy dx equals negative 6x squared y minus 4. Then I'm going to factor out the dy dx and divide by what's remaining here. So the dy dx is going to get factored out as a GCF, and then I'll have this 2x cubed minus secant squared y that I will divide on both sides. So dy dx is going to equal negative 6x squared y minus 4 divided by 2x cubed minus 3 secant squared y. Now, if you happen to work this problem out by bringing the dy dx's to the right-hand side, you'd get the same expression here, except both terms on the numerator would be positive, and the signs of the terms in the denominator will flip. So you'd have like positive 3 secant squared y minus 2x cubed. Letter D. All right, now we're starting to bring in our new derivatives. Okay, now that we know how to differentiate a logarithm with a base other than e, we're going to put that into play here. So y prime is going to equal 1 over x squared minus 4 times the natural log of 6 times the derivative of x squared minus 4, which is 2x. So y prime is going to be 2x over x squared minus 4 times the natural log of 6. Letter E. Okay, here we've got a fraction, so we're going to have to use the quotient rule. Y prime is going to equal the derivative of the top times the bottom minus the top times the derivative of the bottom. All that divided by the bottom squared. And I think I'm just going to leave this one alone. Probably could manipulate this algebraically a little bit. There's not really much that I think is worth doing here. Letter F, arctangent. Okay, so this is going to be one of our new derivatives. Arctangent is, or the derivative of arctangent is going to be 1 over 1 plus x squared. So the derivative of arctangent of 5x would be 1 over 1 plus 5x quantity squared times the derivative of 5x, which is 5. So y prime is going to be 5 over 1 plus 25x squared. Okay, now number 2, we've got some throwback questions. These limit questions are going to take us back to Unit 1. It's been quite some time since we've seen any limit questions. So, please reach out if you find any of these confusing or you just want me to go into more detail on any of these problems. So the 2a wants us to find the limit as x approaches 7. Now, to evaluate a limit, we need to examine what the value of the function is approaching from the left of 7 and from the right of 7. And as we can see here, the left-hand limit does not equal the right-hand limit. The left-hand limit equals 4 from the left, and the right-hand limit equals 1. And since those two things aren't equal, this limit does not exist. Okay, the left and right-hand limit must be the same in order for the limit to exist. So now let's take a look at what's going on as x approaches 3. Well, even though the function is not defined at 3, the value of the limit as x approaches 3 from the left and the right is both 4. So if we look at these two arrows from the left and the right of 3, we can see that both of these arrows are pointing to the y value of 4, and that's going to be our limit there. So f of 7 is the value of the function when x is 7. So let me erase this, kind of clean this up a little bit. Okay, here's where 7 is, and we see we've got an open dot and a closed dot, and so it's the closed dot that we're interested in. The open dot indicates that that value is not defined there. The closed dot says that, hey, yeah, we're actually defined there. This is where we're going to find the value of f. So f of 7 is going to be 1. Part D says that p is defined as 3 to the x times f of x. Determine the derivative of p and then evaluate it at a. In other words, find the instantaneous rate of change of function p at x equals 8. So in order to differentiate this, we're going to have to use the product rule. So it's going to be f prime g plus fg prime. So the derivative of 3 to the x. This is one of our new derivatives. So it's going to be 3 to the x times the natural log of 3 times f of x plus 3 to the x times the derivative of f of x. So that is p of x. That's how we're going to define p of x. And then if we want p, the derivative of p when x is 8, we're just going to plug in 8 into all of these x's. Okay, this f of x, we will be able to evaluate that. We'll come back to that. Okay, so some of these I would not expect you to be able to evaluate. So, like, for example, 3 to the 8th power, that's going to be just some crazy big number. We're going to leave that as just 3 to the 8th. We're not going to mess with that. Times the natural log of 3, that's just a constant, so we'll just leave that alone as well. F of 8 is the value of the function when x is 8. If we look at the graph, and that's what f is referring to here, when x is 8, y is 3. So this is going to be a times 3. So actually, we could probably change this 3 to the 8th times 3 to 3 to the 9th, but I don't think we really necessarily have to. Plus 3 to the 8th times the derivative of f at 8. So what that's referring to is the slope of the curve when x is 8. What's the slope here? And we could do, since this is a line, a basic rise over run check to see what the slope is. And we could see we're going up 2 over 1, so the slope there is 2. I guess I should stay consistent with my notation here. There we go. There's our derivative. I'm just going to leave it just like that. Number 3 says determine the instantaneous rate of change of the function inverse sine of 2x at x equals 1/4. Simplify your answer. So here we're going to have to use the chain rule, and we're going to use our new derivative of inverse sine. The derivative of inverse sine is going to be 1 over the square root of 1 minus x squared. So here, the derivative of f is going to be 1 over the square root of 1 minus this quantity squared, so minus 2x squared, times the derivative of 2x, which is 2. Now I'm going to evaluate that at 1/4. So f prime of x, or not of x, but of 1/4 is going to be the inverse, sorry, not the inverse sine. What are we doing here? 2 times 1 is 2 over the square root of 1 minus, and then this little thing here would be 4x squared. So 4 times 1/4 squared. It does say simplify the answer, so let's see how far we can get here without a calculator. 2 over the square root of 1 minus, let's see, a 4th square is going to be 16, so 1 over 16. Now 4 times a 16th is a 4th. 4 divided by 16 is 1/4. So this thing's going to equal 2 over the square root of 1 minus 1/4. 1 would be 4/4, so 1 minus 1/4 would be 3/4. So we've got 2 divided by the square root of 3/4. And, if you leave it like that, I'm pretty happy if you get that far. But really, we can rewrite this as 2 divided by square root of 3 over 2. And 2 divided by square root of 3 over 2 would be equivalent to 2 times 2 over the square root of 3, which would be 4 square root of 3. So this would be a good answer too. And personally, I'm not a huge fan of rationalizing the denominator if it's not necessary. But if you were to get a multiple choice item, the answers will likely be rationalized. So here, if I multiply by root 3 over root 3, I'm going to get 4 root 3 over 3. So I personally like this answer better, but the AP test is probably going to have their answers rationalized like this. I don't know for sure. Sometimes they do, sometimes they don't. But you should be ready to rationalize if needed. Number 4 says write the equation of the line tangent to the graph at the point 2, 0. So we see that we've got a bunch of y's in here, so we're probably going to need to differentiate implicitly. To write an equation of a tangent line, we're going to need a point we're going to need a slope. So the point is going to be 2 comma 0, and the slope is going to be the value of y prime when x is 2 and y is 0. So we need to find y prime, or dy dx, by differentiating both sides. So the derivative of e to the y is going to be e to the y times dy dx, or just y prime if that's easier for you. Plus, we'll use a product rule here. So derivative of 3x is 3 times y, plus 3x times the derivative of y, which is y prime, plus the derivative of x squared is 2x. So that's all the left-hand side there. I didn't realize it would be so long. I'll go ahead and move that over. Equals the derivative of 2x plus 1, which is just going to be 2. So if I'm looking for the slope at the point 2 comma 0, I'm going to have to isolate y prime and then plug in 2 comma 0 for y. So let's try to isolate y prime. We're going to bring this 3y over to the right, and then, so we'll have e to the y prime plus 3x y prime equals, we're also going to bring this 2x over, 2 minus 3y minus 2x. Factoring out the y prime is going to leave us with e to the y power plus 3x in parentheses. And so we're going to end up just dividing by that sum. So 2 minus 3y minus 2x, all divided by e to the y times 3x. Whew, all right, so let's find that. Let's find the value of this derivative at 2 comma 0. Okay, so let's see. What I want to do here is I kind of want to block this off because this problem kind of took up a lot of this space. And I'm going to move all this over a little bit. And there we go. Now I want to evaluate y prime at 2 comma 0. So I get 2 minus 2 times 0 was just 0, minus 2 times 2 is 4, over e to the 0 is 1, times 3 times 2 is 6. So this is going to equal negative 2 over 6, or negative 1/3. Oops. Whoa. Let's back this up a little bit. This should actually be plus. Sorry about that. Because I've got e to the y plus 3x, not e to the y times 3x. Oh, come on. Mr. Schuler. Get it together here. 1 plus 6 is going to be 7. Whoa, how did I do that? That was not intentional there. Let's bring that down just a little bit. I don't even know how I did that. That's weird. It's not going to let me grab this little piece that I want. Oh, that's bizarre. All right, well, okay. Yeah, I'm not sure how to undo that, but that's okay. We'll just take it from here. This has got to be plus. 1 plus 6 is 7. And so this is not going to be negative 1/3. It's just going to be negative 2/7. So that's going to be the slope. Let's zoom back out here. It's negative 2/7. And so now we're ready to write our equation. Y minus 0 equals negative 2/7 times x minus 2. Number 5 says consider the function f of x equals the square root of 3x plus 1. Determine the derivative by using the limit definition. Oh boy, okay. It has been a while since we've used a limit definition. In fact, this was one of the first things that we learned in Unit 2 when we first learned what a derivative even was. Remember, we had that whole first unit on limits, and it kind of led us up to the very beginning of Unit 2, which introduced to us to the idea of a derivative. And a derivative is just a limit. And so it kind of necessitated the talk of what a limit is. So if we have this function and we want to find the derivative sort of the old-fashioned way using a limit definition, we are going to substitute in x plus h into x and then make this f of x square root of 3x plus 1. we're going to have to look for some algebraic tricks to be able to manipulate the equation and hopefully reduce that divide by h out so we don't have the h approaches 0 and divide by 0 error. So let's set this up. So the derivative, if this is f of x, then f prime is going to be the limit as h approaches 0 of the square root of 3 times x plus h plus 1. Okay, so right now I'm plugging in x plus h into x. And then minus f of x, so minus the square root of 3x plus 1, all over h. So that is the definition of the derivative, but we need to simplify this. And so to simplify any of these derivatives or any of these functions that have square root, we're going to multiply both the numerator and the denominator by the conjugate of the numerator. So we're going to multiply the top and the bottom both by root 3 times x plus h plus 1 plus root 3x plus 1. I'll have to do that both in the top and the bottom. And recall that we really don't want to multiply out the denominator because we do want that h to cancel. And the numerator should be able to be simplified pretty easily because if we multiply these two things together, that is the same expression. And so when you multiply a square root by itself, you're just left with whatever's underneath the square root. So we get the limit as h approaches 0 of h, I'm going to write the denominator first here, times the square root of 3 times x plus h plus 1 plus the square root of 3x plus 1, or the square root of that. Okay, and the numerator, these two things will multiply, and I'll get 3 times x plus h plus 1 minus, and I'm going to subtract this whole next expression, what I get when I multiply 3x plus 1, or root 3x plus 1 times itself. So that will just be 3x plus 1. Now, really what I'm looking for here is for these h's to cancel so that I can actually use direct substitution and plug in 0 for h. So I'm going to simplify the numerator. It's going to be 3x plus 3h plus 1 minus 3x minus 1, all over that same denominator that we had before. Now in that numerator, we can see that we get the 3x's are going to sum to 0. Same thing with the 1 minus 1. And then so we're just left with 3h in the numerator. And h divided by h is 1. So we can reduce these two to 1. And so now we've got this expression, the limit as h approaches 0 of 3 over the square root of 3 times x plus h plus 1 plus the square root of 3x plus 1. And now I can plug in 0 into h. So if I do that to evaluate this limit, then I'll be left with 3 over 3 times x plus h, which is just x, plus 1, so the square root of all that, plus the square root of 3x plus 1. Now notice how we have two of these square root of x plus 1s. So it's going to be 3 over 2 times the square root of x plus 3x plus 1. Now, that took a lot of work, yeah, and what we learned pretty quickly after learning about this limit definition is that there are a lot of derivative rules that we can rely on to get us through that process without dealing with limits and all that. And so we learned a bunch of elementary derivatives, how to differentiate using the power rule, the quotient rule, the product rule, the chain rule, and all that good stuff. And now we can use that here. So if we want to, we're going to confirm our answer by using the chain rule. And so first I'm going to rewrite this f of x as 3x plus 1 to the 1/2 power, just to make it more obvious how this chain rule is going to play out. f prime then is going to be 1/2 times 3x plus 1 to the negative 1/2 power times the derivative of the inside, which is just going to be 3. So f prime is going to be 3 times 1/2, so it's going to be 3 over 2, and then 3x plus 1 to the negative 1/2 power is going to be the square root of 3x plus 1, but in the denominator. And we can see, sure enough, these are the same thing. But look how much easier that was on part B. Yeah. Number 6, determine the points at which the slope of the tangent line is equal to 5/2. So we need to find the slope of the tangent line at 5/2. Oh, wait, let me reread that. Oh, no, determine the point. So we're trying to find the x value when the slope is 5/2. So let's first find the slope. Let's find that derivative. And we'll use the quotient rule here. So derivative of the top is going to be 3 times the bottom, which is x plus 2, minus the top, which is 3x minus 4, times the derivative of the bottom, which is 1. All over x plus 2 squared. Okay, so now I can simplify that numerator. So we get 3, forgot a little equals there. 3x plus 6 minus 3x plus 4 all over x plus 2 squared. And if I simplify that one more step here, just move that over, give myself a little bit more room. F prime of x is going to be the 3x minus 3x, just cancel out, so we just get 10 over x plus 2 squared. Now what we're looking for are the x values that, or not just the x values, but the points. We'll find the y values afterwards, but first we need the x values where the tangent line is equal to 5/2. So now that we have an equation for the tangent line, which is 10 over x plus 2 squared equals 5/2, we can solve this for x. And I'll do that by using the cross products property first. So 5 times x plus 2 squared is going to be 5, well, just that, 5 times x plus 2 squared equals 10 times 2 is 20. If I divide both sides by 5, I'm going to get x plus 2 squared equals 4. And I think actually I'm going to push all this stuff back to the right. So I'm going to work, I kind of want to work downwards here and don't want to impede too much on my space for number 7. So here I can take the square root of both sides and get x plus 2 equals plus or minus 2. And then subtract both sides, 2 from both sides. So I get negative 2 plus or minus 2. So I'm going to have two x values here. I'm going to have negative 2 plus 2, which is 0. And I'm going to have negative 2 minus 2, which is negative 4. And once I get those x values, I can find the y coordinates of the point by plugging in these x values that I just found into this equation. So 3 times 0 minus 4 is going to be negative 4. Negative 4 divided by 2 is going to be negative 2. If I plug in negative 4, I'm going to get, I'll do a little scratch work out to the side here. 3 times negative 4 is negative 12 minus 4 over negative 4 plus 2. It's going to be negative 16 divided by negative 2 is 8. So the two coordinates here are going to be 0, negative 2, and negative 4, comma 8. Number 7 says determine the derivative, and we're going to have to use the our exponent rule here and chain rule. So this is going to be one of our new derivatives where we are differentiating an exponential function, and we get 8 to that secant x times the natural log of 8. Okay, so that's like our outside derivative. And our inside derivative, the derivative of secant. Now, it's been a little while since we differentiated secant, but the derivative of secant is secant tangent. So we're going to have secant x times tangent x. Here's number 7. All right, moving on to number 8. So more derivatives. This is really going to put you to the test. How many more we got here? Okay, we got five kind of major derivatives that kind of put together everything that we know about differentiating all together here. I'm trying to look to see if there's no implicit differentiation necessary here. So we're just going to do some straight explicit differentiation. So 8a. Goodness, look at this. We've got a product. So we're going to have to find the derivatives of each one of these individually. I think this might be a good case. Now that these expressions are getting just kind of out of hand here, I'm going to treat 5 to the tangent x as my f, and log base 4 of g plus 3 is my g. And I'm going to just right above here, I know we've done a bunch of product rule here, but I think it'll be worth trying to rewrite this up here, because what I want to do is I want to write out my derivatives for f and g separately. I think it'll make writing this entire expression a little easier. So f prime is going to be 5 to the tangent x times natural log of 5 times the derivative of tangent x. And the derivative of tangent, as we know, is secant squared. So secant squared x. So that's our f prime. Our g prime is going to be 1 over log base 4 of x plus 3. Oh, what am I doing here? No. 1 over x plus 3 times the natural log of 4. And then we'll multiply that by the derivative of the inside, which actually just ends up being 1. So we don't really need to worry about that as much, because multiplying by 1 is obviously not going to change anything. So now I'm going to execute this. Now that I'm not going to try to do it all at once. I wanted to break it down here so you see the f prime and the g prime, because otherwise this is going to get a little out of hand, this derivative here. I don't even know if I'm going to have enough space to write it. F prime is going to be well, and here's kind of the danger of like marking these as f and g prime, is I don't want you to think, oh gosh, now I kind of wish I didn't use f and g, because this function is called f, and this is different than this f. Maybe what I'll do instead of using f and g here is just use some different letters. Use u and v. I don't know if that'll make this easier or harder, but at least we won't get the f's and g's confused. I guess the g was fine, but the f was really not fine. Oh, I just wrote it again. Gosh, this is what happens when I try to talk and write at the same time. Okay, so it's going to be the u prime here instead of f. 5 to the tangent x, and I'm going to zoom in so I can try to write a little smaller here. 5 to the tangent x times natural log 5 times secant squared x. Okay, that's just the u prime part. That's just this part. Okay, next we're going to do v, which is right here. So times log base 4 of x plus 3. Okay, so yeah, there's the v. And now let's do u. So that's the 5 to the tangent x. So plus 5 to the tangent x times v, or v prime. So v prime is 1 over x plus 3 times the natural log of 4. So hopefully breaking it down like this will help you out. Wait a minute, that should not be plus, that should be times. My apologies. There are a lot of details here, as you can see. So it's going to be pretty easy to kind of mess some of that up. Okay. Let me just take a quick look over this before I move on and make sure that I don't spot any obvious errors here. I've got the file. Yeah, that all looks good. I think we're good to go here. Don't see any obvious errors, so I'm going to go ahead and cautiously box my answer here. That is just bananas, but I kind of like it. All right, letter B. Here we're just going to use basic chain rule. This one's not going to be as crazy. So f prime is just going to be 3 times e to the arctan, okay, times the derivative of arctan. We would have a times natural log of the base here, but natural log of e is 1. So that's why we don't really need that. But the derivative of arctangent is going to be 1 over 1 plus x squared. And you're I'm okay if you leave it like this, but don't be surprised if you get a multiple choice item and it looks a little bit more like this. Okay, so just be ready for that. Letter C, got inverse sine of 8 to the x. So first we'll start with the outside function, which is the inverse sine. And so f prime is going to be 1 over the square root of 1 minus 8 to the x squared times the derivative of 8 to the x, which is 8 to the x, times the natural log of 8. And that's pretty good. I'm going to go ahead and rewrite this as 8 to the x times natural log 8 all over the square root of 1 minus 8 to the 2x. Now, letter D, arc cosine of x cubed. So this will be worked pretty similarly here. The derivative of arc cosine is -1 over the square root of 1 minus the thing that's on the inside squared, so then in this case x cubed squared, times the derivative of the x cubed, which is 3x squared. And so I'm going to bring that 3x squared up top here, -3x squared divided by the square root of 1 minus x to the 6th. And this brings us to our very last problem, okay? The natural log of arctangent of x. So we'll start with the natural log derivative, which is 1 over x. So 1 over arctangent x. And normally we'd have like a times natural log of the base here, but natural log of e is just 1. So we could just fall back on the good old natural log derivative that we know and love, times the derivative of arctangent, which is 1 over 1 plus x squared. Now you can multiply these straight across, so we can rewrite this as 1 over arctangent of x times 1 plus x squared. You don't have to bring them together like this, but if you do, make sure that you put that 1 plus x squared in parentheses. All right, so this was a pretty decent homework here. Hopefully you didn't get freaked out too much when we brought back those that limit definition question. It is good to kind of go back and practice that algebra, if nothing else. But anyway, thanks for watching, and y'all have a great evening.